Okay, guys, welcome to Smarter YouTube playlist. So today I will show you how to do statistical downscaling, but this one is for bias correction. So we will do bias correction by using linear scaling and empirical quantile mapping. So without further ado, I will show you the code in R that I have prepared for this one. Let's share the screen, entire screen. Okay. Okay, now we go for linear scaling first. So here we will do a bias correction for daily data. But this code you can customize for monthly data also. But in this case, we use for daily data. So we use the linear scaling to bias correct the GCM so that it will simulate later according with the historical data set. So first, for linear scaling, we need library dplayer, and then put your dataset in your working directory. So in this case, I put my dataset here in this working directory. You see a lot of data is already here, and there's some output already. I have tested this code, and it is working very well. And then what we need here is that we need a historical dataset. So here we use CHIPS dataset. And then we also need historical GCM because we want to bias corrected the historical GCM, the raw dataset of GCM, and bias corrected it with the historical CHIPS dataset. So we need this CHIPS dataset and GCM dataset. So for example, I will show you how the CHIPS dataset looks like. So this is our dataset. I have 44 grid point here. This is actually for one of the basin in Sarawak, only 44 grid point. That's why it's only 44 because this is only for a small basin in Sarawak, which is Batang Ai Basin. So this is CHIPS dataset from 1981 until 2014. Because we want to bias correct the same IP6. So I prepare data like this. I have year, month, day, and then V1 until V44. So this is our input data set. I have grid 1 until grid 44, year, month, and day. Similarly, we have our historical GCM dataset. So historical GCM dataset also you arrange similar with the observed dataset. You have year, month, and day, and then 44 grid point V1 until V44. So similarly, this dataset also from 1981 to 2014. Make sure that it is the same, have the same. For example, here until 12,414, 419, and this dataset also 12,419. So make sure that there is no missing value, no missing that, because sometimes GCM they have missing value in the historical dataset, and you need to fill that by using forward fill method that I show you in the different tutorial. So we have this input dataset. That's all we need. First here, we also need future GCM. For example, here we have SSP1. I use SSP2, SSP3, and SSP5. So for SSP1, make sure it is the same arrangement from year, month, day, V1 until 14, from 2015 until 2100. So the same thing with all other GCM. I have SSP1, 2, 3, and 5 arranged the same way. So read that dataset. Now we add day of the year column for matching daily scaling factor. So we use this code here as numeric. We put it as numeric format as date, past, chips year, chips month, and chips day. So we use this code to add day of the year column to match the daily scaling factor. And then GCM DOY as numeric format as date, past, GCM year, month, and day. Okay. Now for future projection also we do the same. You can see it's quite lengthy, but it is the same code, more or less. I need to put it a little bit like this. Okay, so everybody can see it. If you cannot see it, increase the resolution of your your viewer in YouTube, and you will be able to see this code. And then as numeric format, as that PES, GCM1, GCM2, GCM3, GCM4. So we add day of the year. Because in this method, we do linear scaling. We not take the mean of the data set because we want to make a linear regression scaling factor for each month. For each month, that is the way doing this one. If you don't do it by by month, you will get a very not good result. Not good. You cannot use that kind of result for linear scaling. So then we identify rainfall data column dynamically. So we have the column now, year, month, day, and DOY. So we just exclude non-rainfall column here. Set diff names chips. Now we compute daily scaling factor based on the OI. So we make linear scaling day by day because this one is daily data set. If we use for monthly, it will be month by month. But this is for linear scaling. For daily, we do day by day. So linear scaling factor is chips by DOY. We summarize all mean, and this is all the equation for compute for daily dataset. We use a scaling factor based on the OY here. Okay, you use this code, you run this one. It's very fast, I think. Okay, now we put the function. This is the calculation for linear scaling. So we can see here function to apply daily linear scaling correction. So we use function GCM data, scaling factor that we use, and then corrected GCM and GCM data. And then for D is 1 to 365 day, extract scaling factor for the given DOY. And then ensure dimension match before applying correction here. And if there is mismatch, it will give you some warning. But I believe there is no warning here. And then I want to remove the OY column before returning the corrected GCM because we put the OY just now, right, for calculating the linear scaling for daily dataset. And I don't want the output also have the OY because we want to have a clean output, just the result of linear scaling. So we run this one. This is depend on your laptop. I think it can take some time. Oh, it's very fast. Very fast here. And then apply correction to historical GCM. Now we apply that correction just now to daily GCM here. This one is why error in select? It's okay because we don't want the OY. Now we write this one. Corrected GCM. So now we have corrected GCM daily linear scaling. So let's see corrected GCM daily linear scaling. So we have here, this is the corrected GCM, year, month, and day. And then in the end, there is no DOY. So this is good. You can use this result for. And then now we have correct the GCM, right? The historical GCM. Now that relationship we use to correct the future. So we apply correction to future GCM here for GCM 1, 2, 3, and 5. So we do correction here for all that 4 SSP that we use. So if there is error in select the OY, then you just ignore that one because we already remove the OY. We don't want to have the OY at the end of that result. And then now we just write that, save the future projection that we have. Okay, now I put it LS, corrected GCM 1, 2, 3, and 4. Okay, now this is the result LS for GCM1. It have corrected the GCM future projection. Future projection is corrected here. And then this one also, GCM2. Okay, it has this in the end it put scenario. in the end here, scenario. So just remove this one. We don't want this scenario data set in the end. Just remove this one because we want to check this data also later on. Make sure you don't have this additional column. We want only the result. Okay. Okay, remove this scenario. Let's check the result. Make sure that it will be different. It's supposed to be different. It's different. You see, it is different, so it's okay. So the result is good. It is already a dual linear scaling. So this is empirical. I will explain later on. I will explain now. So now we go to empirical quantile mapping for daily data. So usually linear scaling is not very good. Yes, I believe if we publish paper, it can be used for comparison. It's okay. Linear scaling usually is very good for monthly data, and they have many drawback of this linear scaling. It's good in terms of correcting the systematic bias, but it's failed to capture the trend for future projection. But usually the empirical quantile mapping is usually better than linear scaling, but it's depend. I don't know. Sometimes linear scaling can be better than empirical quantile mapping. Sometimes empirical quantile mapping better than the linear scaling. This different study area will have you different result. You need to justify why it's better or not. So for empirical quantile mapping, this is also for daily data. We use deep layer and QMap for quantile mapping, and then we use the same data set just now. We use in the same working directory. So chips data set, we have Batang I grid point basin, and then we use the similar GCM, raw GCM for historical, and similar future GCM for SSP 1, 2, 3, and 5. But if you have less GCM, you can just put dummy data or something like that. It's okay. Put it here if you don't want to revise this code. But it will works okay. Now similarly we identify rainfall data column dynamically, year, month, and day. And then we function to apply quantile mapping correction. So we apply quantile mapping correction function, observe GCM, future GCM. We correct GCM data, and correct future GCM here for column in rainfall column. We extract, observe, and GCM series for the given column. So we have observed data and GCM data. And then we fit quantile mapping model, which is empirical method. So quantile mapping, they have gamma quantile mapping. We have empirical quantile mapping. So in this case, we use empirical quantile mapping. This is take it very particular because there is different quantile mapping out there. So the method we use is RQuant here. So Q step is 0.01. We fit quantile mapping, observe, and GCM series. And then we apply that correction to historical GCM, do QMap for correct the historical GCM by using quantile mapping, and then apply that correction to the future GCM also. And then we return the list of this GCM for corrected GCM and corrected future GCM. So we run this code. Rainfall columns already run. So we run this. It can take, here it will take. Apply quantile mapping correction to historical and future GCM. It will apply here. So this will take some time, I think. Let's see how long it takes. It depends on your laptop. But quantile mapping usually being argued is better than linear scaling. But you can do a statistical assessment or something like that later on, and I will show you how you can do PDF, you can do Taylor diagram, target diagram, and so forth in this code. So it will be very comprehensive. You can try to see the result of your bias correction. Okay, now quantile mapping is running for the final GCM. So happy Ramadan for everybody that is celebrating Ramadan. So it's almost finished now. Quantile mapping. Now it's run for historical future one. Okay, now it's finished. Now we save the historical GCM that we have corrected. So the corrected one is corrected GCM daily quantile mapping here. So whatever here, it will replace it with this new data set. So you see here, this is the corrected GCM by using quantile mapping for historical one. Now we print for the future projection. This is for SSP1, SSP2, SSP3, and SSP5. And then successful everything. So we can see here, this is the output. Here Monday. So this is corrected quantile mapping for daily time series. Okay, we have this GCM4, which is SSP5 also here. So it's okay. Now we want to plot we want to check our result, right? Is this correct or not? If we look only in the number, it can be quite difficult. So I plot the time series for this one from historical to future. So we can compare. First, we look at the linear scaling. So I put here linear scaling. Okay. So we need ggplot2 data library, dplayer, and tidyr, and then the same working directory. And then we read our chips dataset, corrected GCM, because we want only the observed and the corrected GCM, and then our future corrected GCM for linear scaling. So we have this chips grid dataset, and then corrected GCM for linear scaling, and then let me check first. Okay, linear scaling, and then GCM 1, 2, 3, and 4 for future projection. So we run this data set, and then we add scenario label here for chips, historical GCM, SSP 1, 2, 3, and 5. And then we combine that data set just now. We combine that data set, chips, corrected GCM future, corrected GCM 1, 2, 3, and 4. So we want to make historical chip, corrected GCM, historical, and then future projection for future projection. So, and then we convert year, month, and date to a date format. Here, all date is as date here. Okay. Now we select one rainfall variable for plotting. So, and then we plot this time series. So it takes only one variable. I think it's only take maybe one what we call. So this is the result. You can see historical GCM has been corrected, and then daily data. You see daily data, it looks like this. It's not looks very good, right? Especially for the corrected GCM. It's because okay. And the way that we want to better plotting compared to daily one is usually we plot it monthly so that we can see the pattern more clearly. For this one, we do monthly. Usually when we do validation of the corrected GCM or something like that, we take the monthly data. It's easier to look at the pattern compared to daily one. So let's do this for monthly dataset, the same working directory. We use the same input dataset, chips, corrected historical GCM, corrected GCM future projection 1, 2, 3, and 4, and then add label scenario, similar one just now. And then we combine dataset for chips, corrected GCM, and then future projection, corrected future projection, and then convert year and month to a proper date first day of each month. And then we select a rainfall variable for plotting, which is, I think this is V1, V1, something like that. And then we compute monthly rainfall. Because we don't want daily data, now we want monthly rainfall. So we take the mean rainfall here. Okay, now we plot. Let's check first. It's not supposed to be mean here. It's supposed to be sum. It's supposed to be sum. Let's check again. Okay. When it become sum. It's supposed to be sum. Sum. There is monthly rainfall time series. So this will be rainfall. So the plot will be in monthly. You can see the pattern is how GCM is being corrected, and then the future projection. Rainfall usually look like this. It's very messy. It's not temperature. You cannot expect there is different, very different projection. And this area is very small, so the projection usually very similar. We see the projection also not very distinguishable, right? Because rainfall like this. So you need to there is some way we can plot this. For example, here I will show you how we can plot this one. I prepare all the code here for daily and monthly one, and you can look at the statistic. This is usually when we publish the paper. When we publish the paper, you need to compare the statistic between the GCM and corrected GCM. So we use as a statistic. For example, for this one, we will use matrix and Hadir-Graph packages in addition to the player. So we use the same input dataset. So we use chips dataset as the historical one, and then chips we will compare with GCM or GCM we compare with chips, and then corrected GCM we compare with chips, and we want to see which data is better after correction or before correction. How much is become better? So we identify rainfall column dynamically year, month, and day, and then we aggregate daily to monthly data because we use daily data here, but we want to make statistic for monthly data. But if you want daily data, I have prepared this one, daily data up here, and then this is for monthly data. So we use function to aggregate daily to monthly data here by using this code, and then convert daily to monthly, aggregate to monthly, and then aggregate to monthly with function. Then extract rainfall matrix for statistical evaluation. So we have as matrix first, convert it as matrix, and then compute goodness of fit matrix. So we use GOF function. So for GCM and corrected GCM. So this GOF function is very good. You get a lot of statistic. I will show you later, and then put it as a data frame, the result as data frame, and then assign column names from V1 to Vn, because we have V1 until V44, right? And then save this result for monthly dataset. Okay, now we have validation. So validation here, GCM here. Okay. Yeah, you can see all the result for validation that you want for grid 1 until grid 44. Each grid. If you want to take the mean, just take the mean. It's up to you. It's easily calculated. But usually we show the range of the error, like 0.13 until negative or something like that. And it gives you a lot of metrics here from ME, MAE, using GOF function, MNSA, DR. You can check online what is all of this mean. DR2, VE, volumetric efficiency, KGE, a different type of KGE, modified degree of agreement. There are a lot of metrics you can get from here. and then you can compare. And this is the monthly one. You can see mean error, mean absolute error, something like that. And then because we want the monthly one, right? GCM. This is corrected GCM. This is the corrected GCM by using linear scaling. Okay. Okay, now we do PDF. PDF is very important one. We want to compare the performance of our corrected GCM just now. We use ggplot2, reshape2, and dplayer, and it's the same working directory. And the input data will be the original chips dataset, and then the raw GCM and the corrected GCM. Because we already prepare for linear scaling and quantile mapping just now, right? So you can put any dataset. For example, I put quantile map linear scaling first. Let's see, corrected linear scaling. So we have corrected linear scaling. Okay, we run for linear scaling first, and then convert this convert wide to long dataset for chips using math function, year, month, day, because we want to do for monthly one, and then GCM long merge it into long format, and then corrected GCM also convert it into long format. So we merge that dataset for comparison, merge that dataset chips with GCM, and another one chips with the corrected GCM. Okay. Okay, now it's merging the data. Okay, now we compute total monthly rainfall per grid point using sum. Okay, now we convert to long format for plotting here, PDF. It will form the PDF, and then we plot it. Okay, plot PDF. So this one for linear scaling. You can see corrected GCM, the blue one perform better compared to compared to GCM, right? You see the GCM is the red one. It seems underestimate compared to the chips dataset, but the corrected GCM seems to be improved in terms of the peak here, the peak, and also the right tail. Try to simulate the chips dataset. So you can see the performance here, and we can also compare with quantile mapping. Our result corrected GCM with quantile mapping. This one, quantile mapping. Okay, and then we can run all this code. Just change the input data because the arrangement is all the same. And then it will show you the performance for corrected GCM for quantile mapping. See, it doesn't seem to be very good quantile mapping. Empirical quantile mapping is seem to be lower, but the shape is better. But in terms of underestimation is there. So this is some other PDF. This is for future one. So this is for linear scaling. You can run this code to show the performance of linear scaling for future dataset. You compare between, this is for daily one, but usually we show for monthly one. For monthly, we can see the difference between the GCM. As you see, SSP5 is higher rainfall compared to SSP1, and SSP2 also higher rainfall. So different area, different study area, you will have different kind of result. This is how we want to compare the future projection. And then we have target diagram. This is for, target diagram is we want to see the metrics also. You can run this code. This is go for monthly one. Go for monthly for validation. Target diagram. I will show this in different tutorial. It's been quite long already for this tutorial, but I will just show you the result. Yeah, you can see it will show you the result for normalized bias, normalized RMSE, and the size of R square value. So the location is which is located in this target diagram to see the performance of the GCM and corrected GCM. And you can just change the input data here compare with the quantile mapping. If I put quantile mapping here, let's see. I'm also curious about this one. Let's see for target diagram. Okay, you can see quantile mapping. This quantile mapping. Quantile mapping seem to be perform better. And now we look Taylor diagram. Taylor diagram go for monthly also. This is another way to show the result. So I run it. Just put the same data set, daily data set for linear scaling here. You can see the performance. You see the GCM corrected for linear scaling seem to be not good. Yeah, in terms of standard deviation, it's not good. But if we use quantile mapping, let's see, quantile mapping. Quantile mapping seems to be better. It's lower standard deviation, and also correlation is also better, 0.5 compared to raw GCM. So I think it's better to use empirical quantile mapping compared to linear scaling. So you can use Discord for your study. Just check it out. Look at this tutorial because all the visualization in the end here, there is daily one, there is monthly one. You just need to change the input data for corrected GCM here. Everything is all the same. All the input you just change with your input data that you get from linear scaling and quantile mapping. I think that's all for today. Sorry I little bit late on this one because so many works to do. Thank you for watching.